Hello, good people. We're back. So this is chapter 11. And if you're curious, we're only doing chapter 11 and 13, sort of just to save a bit of time in English. Chapter 12 is very similar to chapter 11. It's just using repeated measures, Anova. It's very similar to the last two chapters. So chapter 9 and 10. Chapter 9 was a one sample test. Chapter 10 was two sample tests, independent and paired. While chapter 11 would be sort of an independent ANOVA, chapter 12 would be sort of a repeated measures ANOVA. So the logic is exactly the same. It's just a different set of equations. So I'd much rather have you spend the time figuring out ANOVA, which is an independent sample process. And if you really understand the independent version of ANOVA, then you'll be able to understand the repeated measures if you ever need to do that. So that's why we're not doing chapter 12. In chapter 13, we'll get to a factorial ANOVA, which will be probably the most complex thing we'll do this semester. But let's start with chapter 11. You got to really understand chapter 11 before you understand chapter 13. So spend more time understanding the logic of ANOVA so that you can really understand the logic for chapter 13. Okay, so like I just mentioned, chapter 10, take two samples, compare them to each other. Chapter 11 is analysis of variance, and so it's kind of the same thing, but kind of different. So we call it analysis of variance. It's because we want to know how different groups vary, and if they vary differently, then we say that they're different groups. They're from different groups, and so we kind of always want to say that. We kind of always want to figure out if a group is different from another group versus not. So that's kind of what we're using to understand what analysis of variance, because it's not necessarily just an average that we need to compare. We're actually comparing the variances and the average, which the average goes into when it comes to the variance. So that's what the analysis of variance is ANOVA. So one-way analysis of variance, which is what we're talking about in chapter 11, one way means only one independent variable. So we've been talking about the examples we've been talking about in class so far. It's been, drugs and symptomology. So if we go back to the good old Alzheimer's drug and symptomology kind of situation, we have one independent variable, it's drug, having an effect on a dependent variable, symptoms. Well, if you're going to create groups, you could say, all right, well, one gets the drug and one doesn't get the drug. And so you'll have two different averages there. So if you have two different averages there, then you're doing an independent t-test if you're using different people and they're randomly assigned and that kind of stuff. But what happens if you said, well, instead I want to use no drug. One group gets no drug, gets a placebo. One group gets 5 milligrams. Another group gets 10 milligrams. Another group gets 20 milligrams. Well, all of a sudden you got four different groups. Well, if you got four different groups, are you doing an independent t-test? Well, what we just learned from last chapter, independent t-test, you got two averages, you got two means, you're comparing them. And now you got four averages. So what are you supposed to do? Well, if you got four averages, and again, you only got one independent variable. So what does that mean? What I'm talking about is you're looking for the levels of an independent variable. So this is when we got to take a step back and say, all right, what's our logic of our research? So we've got one independent variable, it's drug. There's different levels of the drug, but it's still just drug. So if we've got levels of one independent variable and we got more than, if we got three or more, you look down this very bottom, use to find differences between three or more population averages, then you use an ANOVA. And so we'll talk a little bit about that logic here in the next slide. But if you have three or more, i.e. more than two, you have to do an analysis of variance first. Eventually, we're going to do something that's very, very similar to t-tests. They're going to call them paired comparisons, and we'll see that here in a second. But eventually, we'll get to the specificity of looking at a difference between two different groups. It's just ANOVA takes a step, sort of a broader step back first, does a test, and then goes into specifics later. So if you've got three or more averages, you got to do a bigger test to begin with. Then you can dive into the specific comparisons later. You'll understand what that means when we do the worksheets and the rest of this video. So a couple more examples. I've been using the Alzheimer's and symptomology. Another example from your book was people with phobias received 4 different types of treatments. So again, you can see this in the real world. If I was a clinical psychologist and I specialized in phobias and I wanted to do research on them, I would find 4 different psychologists and find out what kind of therapies they're using to treat phobias, and then I would measure their effectiveness, and I would compare all the groups. And so I'd had 4 different groups, so I'd have 4 different averages, and so I'd have to compare all 4 different averages. Another example from the book, I think, was talking about suicide rates compared to countries that were low, medium, and high degrees of modernization. Like, what does that mean? I don't know what that means. It just means you've got a suicide rate from a low country, you got a suicide rate from a medium, and you got a suicide rate from a high, which means you got 3 different averages, which means you got to do an ANOVA. So again, if you only got 2, do a t-test. If you got 3 or more, you're doing an ANOVA first. And so when I say you got to do an ANOVA first, what does that mean? That means you have to do a broad, big, well, I might as well start using the term, an F test. So if you look down here, apparently after the bullet or the dash, now we restart. At number 2, calculate the F value. It's an F test. The F test is a big, broad umbrella test that you do before you do a bunch of t-tests. And so I need you to understand that we're going to be doing what we learned in Chapter 9. It's just we're going to do a test before we get there. And this F test is a big umbrella test that tells us big picture ideas. All right, so let's talk about the logic of the big F test and ANOVA test to begin with. So we're using null hypothesis statistical testing here. This is what this NHST means. Number 1, start by assuming the null is correct. Well, before we used to have a sample 1 versus sample 2. They're equal. That's our null. We only had 2 averages. Well, what happens if we have 4 averages? Well, if we have 4 averages, we assume that they're all equal to each other. That's the null. That's the first F test logic of ANOVA null hypothesis. So that's what this question mark means. You can go for as many averages as you want. This could be 5, 6, 7, 8, however many you want here. So you start by assuming they're all correct. So if you start by this statement right here, 1 sub 1, you see 1 is equal to 2, which is equal to 3, which is equal to 4. In essence, that means 1 is equal to 2, but 2 is also equal to 3, which means 1 is equal to 3, which means 1 is equal to 4. That means they're all equal to each other. That's our first test. And so let's just stop there. The F test just says, do we accept that or do we reject that? All right, so what does that mean? That means if we accept that, that means that if we accept, or I guess I don't want to say accept, if we retain the null, if we retain the null, that means we are retaining the idea that they're all equal. Well, let's look up here. Let's just say, for instance, 1 is not equal to 2, but 2 is equal to 3, which is equal to 4, which is equal to 5. So 2, 3, 4, and 5 are all equal to each other, but 1 is not equal to any of them. If 1 is not equal to any of them, we would reject this null because they're not all equal. All right, so let's use the phobia example here for this 1 through 4. So let's just say this first one is cognitive behavioral therapy. Number 2 was psychodynamic. Number 3 was humanistic. Number 4 was, I don't know, self-help. So cognitive behavioral therapy was significantly different. We would say is different. Let's not say significant. If it was different from the other, the psychodynamic, humanistic, and self-help kind of stuff, if it was different, we would have to say this whole null is rejected. But the F test just tells us do we retain or reject. It doesn't tell us exactly where the differences are. And again, I'll show you that here in the output in the next couple slides. The F test doesn't tell you where, is it 1 versus 3? Is it 3 versus 4? That's different. Is it 2 versus 4? It doesn't tell you that. It just says that they're either all equal or they're not all equal. That's when we have to do that follow-up study, do some follow-up research to find out where the differences lie. So this very first F test just says, do we retain that they're all equal or do we reject that they're all equal? That's it. So some of you might be thinking to yourself, well, why don't we just use multiple t-tests? So in theory, if I've got 1, 2, 3, 4, I can do 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, and 3 versus 4. So how many is that? 1, 2, 3, 4, 5, 6. So that's 6 t-tests. Why can't I just do 6 t-tests? Like that kind of stuff. Well, what happens instead of having just 4 averages? Let's say we had 15 averages. We had 15 levels of the independent variable. That would be 105 t-tests. So if we ran 105 t-tests, we got to go back to this idea that we were talking about last chapter, this chance of type 1 error. So if a type 1 error is rejecting when we should be retaining, we're sick. Again, go back in time. Our p-value that we accepted, or we were told to accept, p of less than 0.5, that is sort of assuming that 5 times out of 100 we're going to reject when we should retain. So it's a type 1 error. So we're making an error. So out of 100 times, 5 times we'll make an error. Hopefully 95 times we'll be fine. But if you do 105 tests, that's basically saying you're going to find 5 significant differences that are probably going to be incorrect. So that's not cool. Like, you can't just do 105 tests and you're like, oh, look, I found 5 significant things. Like, well, no, you basically type 1 error your way into significance, which we can't do. So a whole bunch of probably old, dead mathematicians came up with this idea that's saying, all right, how do we control for that problem when it comes to type 1 error if we have this many F tests or this many T tests? Well, they use a different distribution, so they created an F distribution. We are not going to go anywhere near as understanding what the F distribution is as we did the T or the Z. So what I need you to understand is that we use a different distribution. So what does that mean? We use a different calculation, but we kind of follow the same methodology. We just use a different number. We call it the F value. So we're going to create an F value. We're not going to create the next value. This is why you're in my class as opposed to Kellogg's, which is super awesome, because I'm not going to make you calculate an F value by hand. I'm just going to want you to interpret the output that's going to be given to you. So when it comes time to doing your homework, look up all the F values. I just need you to interpret everything. I don't think you're doing any calculations except maybe for effect sizes in this chapter. So you follow the same process. You calculate an F value of your sample. If it's farther, if it's more extreme into the F distribution, like if it's by the tail, less than 0.05 probability, like that really small area of the tail. If it's really, really high, you reject the null. If it's less than the critical value, you retain the null. And again, this is going back to what you learned from chapters 9 and 10. Like, you find that critical value from the distribution. If your critical value is smaller than your obtained value, then your obtained is less likely, it's more extreme, you reject that they're the same. If that happens, you calculate an effect size. I don't even think I'm going to make you calculate an effect size. What I'm telling you right here, this is the logic. There's an effect size for an F value. I don't think it's super useful, but I just need you to understand that it's out there so you know the difference. But there's an effect size for an F value. I don't know how to tell you this, but besides just telling you, like, I think it's dumb. And then you got to tell the story. You got to interpret. We reject the null only means that there are not equal. Tell me which ones specifically are statistically significantly different. So as soon as you reject, I want to know where the difference is. Is it 1 versus 2? Is it 1 versus 4? Is it 2 versus 3? Tell me where the hell it is. If you retain, you stop. You're done. If you retain the null, like let's just say we did phobias and all these phobias had the exact same outcomes. Well, then you stop and you go, I'm a dumb researcher. I didn't find anything of significance. I measured 4 different things and I assumed something was going to be different, and they're not. So we retain the null, everything's equal. I'm done doing any more research. That's kind of what it is. Most of the time, you'll find a significant F test because you're going to find significant differences because you're doing so many comparisons. You're probably going to find something. All right, so you might want to listen to that a couple times to make sure you understand the logic of Anova. Again, this is just the F test, the very first overall F test you do, the first step of Anova. All right, so if we're calculating an F value, we got to find an F obtained, then we got to relate it to an F critical. The F value, this is where we start getting into why it's called an analysis of variance. Your F value is basically the variances. It's a fraction between 2 different variances, and so the top number, if you remember, is the numerator. The bottom number is the denominator. So the top number, numerator, the variance of the means between groups estimate. whereas the denominator is the mean of the variances. You're like, what? Variance of the means versus mean of the variances. You're like, okay, what the hell does that mean? All right, so if I was actually in a classroom right now, it would be a lot cooler. Basically, I would be running around the room right now saying, all right, one half of the room is a group, and the other half of a room is a group. And let's say there are two other groups in the room. So imagine we're back in our classroom, and you know how we separate the two sides of the classroom. So imagine, and there's the exact same classroom next to it that's the stats lab or the computer lab next to it. So imagine we have that. So we got 4 different groups. So I got, I think it's like 12 people in each group. So what does that mean? I got 48 people in my study, and I got 4 different levels. And so let's just say we're going to try to figure out, let's say if alcohol consumption affects test scores. And so one group of you is going to get a placebo. You think it's alcohol, but it's not. One group is going to get 1 shot. The next group's going to get 5 shots. The next group's going to get 10 shots. So now I got alcohol affecting test scores. I got 4 different levels: 0, 1, 5, and 10. So the numerator, the variance of the means, the between groups estimate. So what does that mean? That means the variance of the means. So what that means is it's taking the variance between all of the averages of all 4 of those groups. So let's just say you're one of the 12 people that didn't get any booze. You're in the placebo group. So there's going to be variability within that group. So say there's 12 of you. I'm going to give you a stats test. There's 12 of you in that group. I'm not going to give any of you alcohol. There's still going to be variability of test scores in that group. You with me on that? I mean, some of you are going to know stats a little bit better than the others, so there's going to be variability. The same thing with the group that gets 10 shots. So if there's a group that gets 10 shots of alcohol before taking the test, there's going to be variability in test scores there. That numerator is the variability of the variance of the mean. So the mean of group 1 versus the mean of group 2 versus the mean of group 3 versus the mean of group 4. It's the variance of those means. And so what does that mean? I want very little variation within those groups of the average. So those of you who did not get any booze, I want all of you to score a 95 on the exam. And all the people who got 10 shots, I want all of them to score a 50 on the exam. So I want little variation in the averages within those groups. Sorry, that's sort of the denominator. So I still want little variation within those groups, but I want high variation between those groups. So what does this mean? So the group that's got 0 alcohol, I want them to be very, very different from the group that got 10 shots. I want them to be very, very different from the group that got 5 shots. I even want them to be sort of different between the 1 shot or whatever. I just want them to be different. And so that numerator is that difference between those groups. The denominator is the error within those groups. So I want very little error within the group, but I want big differences between the groups. So the numerator is how big the number is between the groups. The denominator is how variable people are within the groups. So and so what does that mean? If the numerator is the variance between the groups, that means I want a big variation between the groups. I want the no booze to have a lot of variation between the lot of booze group. So I want that to be a big number. So if that's a big number, that's a numerator. And what do we know about bigger numerators? Bigger numerators end up being bigger scores. And again, if you start thinking back to I want a F obtained to be big, that means it's more extreme, which means I get to reject. So the bigger the F value, the more likely I'm going to reject. So the bigger the F, the better. How do I get a bigger F? I get a bigger numerator. How do I get a bigger numerator? I get bigger differences between groups. The denominator is the error within all the groups, and again, the error all across the groups and within the groups too. I don't want somebody in the no booze group to get a 50 on the test, because that means it's not booze that's driving these numbers. So this is what I'm talking about. I want everybody to score around a 95 in that group. If there's a lot of variability there, that means my denominator gets bigger. My denominator gets bigger. My whole number F test gets smaller. I don't want that. I want a big F. I want a big F because I want to be more extreme. So if you want to get real crazy on the very bottom here, the variance of the means divided by the mean of the variances. If you understand that, you're well on your way to understanding the ANOVA. It's there for those of you who want to have a thought puzzle to work through your head. It's very accurate. I understand what that means, but if you want to spend some time on it, go right ahead. But I just need you to understand the difference between the groups goes on top. The difference within the groups go on the bottom. I want very little variation within the groups. I want big variation between the groups. That's how I know it's the booze that's doing the test scores or whatever it is that my independent variable is. All right, so this is just some nomenclature about the terms. If you see an SS, it's the sum of squares. If you see S hat squared, it's the mean square. Grand mean is the average of the entire sample. If you see the subscript tot or tot or whatever the hell you want to call that, that's the subscript that stands for all the numbers in the experiment. So the sum of all the x's total is all the x scores. T is a symbol applies to the treatment group. So you got N, T, whichever one got the treatment. So if you got treatment 1 versus treatment 2 versus treatment 3, that kind of stuff. That's just the number of scores in treatment 1 group versus treatment 2 group, whatever. This is probably the most important one, this K. Number of treatments in the experiment. It's the level of the independent variables. K is going to be important. And it's basically, so in my design I just talked about in the last slide, if we're talking about booze and test scores, K would be the number of levels of my independent variable. So my independent variable is alcohol. But how many levels do I got? I got 4 levels. I got 0, I got 1, I got 5, I got 10. Same thing with the phobias. You got cognitive behavioral, you got psychodynamic, you got humanistic, and you got self-help. Like those are 4 different levels. So that would K is the number of levels of your independent variable. And the F is the F test from the Anova. So you might just need to be slightly familiar with these terms. All right, so let's talk about the book example. What is this about? I don't even know. We got drugs? Awesome. So there's an example in your textbook that was talking about 3 treatments. So you got 3 different levels of the drug. I was prepared to talk about reinforcement schedules with birds. Sorry. Anywho, who cares? Doesn't really matter. Let's say I've got a placebo drug. I got 10 milligrams. I got 100 milligrams. 3 treatment. Drugs is the treatment. When I'm looking at this degrees of freedom 2 is where I got this 3 treatments. So that's N minus K. Or I'm sorry, K minus 1. Sorry. K is the number of levels. So we got 3 treatments. So it's 3 minus 1. That's where I get my first degree of freedom. I've got 4 subjects per treatment. So you take the total number of people in your groups. So your N total. So we got that N tot. So if I've got 4 subjects per treatment, so I've got 3 different groups, so I got 12. 12, and I got to subtract K is the number of levels I have. So I've got 3 levels, 12 minus 3, that's where I got that 9. So again, this is how you find a critical F. I'm not necessarily going to want you to look up the critical F. I just want you to interpret the F. So what does that mean? If your homework, I don't think any of your homework questions ask you, but if they do, look up the critical, look up the F. I want you to pay attention to how to interpret. Do you know when to retain or reject? So I want you to be familiar, like you'll see critical values for alpha levels of 0.5 and 0.1, very similar to last chapter, and you'll see them that way. So I'll show you here in the next slide what that really means. If reject and null, the only thing you could say is they're all not equal. You don't get to say where they're unequal yet. You just say that they're all not equal. That's very important. Again, the F test is very broad, very all-encompassing. Are they all equal? They're not all equal. That's it. All right, so this is an ANOVA summary table. So this is the very first thing that you need to do when you're doing ANOVA to find out if you retain or reject the null, the grand null, the overall null of an ANOVA, that they're all equal or they're not all equal. So for this example, if we're talking about drugs, again, if I'm just looking at the summary table for the very first time, what can I tell? I can say that I know I'm dealing with a one-way ANOVA because I only have one p-value and I only have one independent variable here. So this is where the independent variable is going to be. Again, I don't really need you to care too much about this sum of squares and this mean sum of squares. But you will see degrees of freedom of drugs 2. I know I've got 3 different levels of drugs. This actually tells me roughly how many people I have in my study. And if you really want to go total is the number of people in my study is this plus 1. So I know I've got 12 people down here. All right, so what I need you to understand, this is where you got this 11.26 is 30.33 divided by 2.69. So you got an F value, 11.26. Great. I don't know where that lies. Well, if you follow the logic that we learned from last chapter, you got this is your obtained F, and you got to find out what the critical F is to reject or retain. And what's kind of cool is that they put it down here. So you've got an F of 0.01. So you've got a p-value of 0.01, degrees of freedom of 2 and 9. The critical is 8. So if I was in the classroom right now, I'd be drawing a data distribution or a frequency distribution or whatever, a distribution, a hump. And I'd throw 8.02 and throw a line down it. And I'd say, all right, this is the critical for an 0.1, significance of an 0.1. Then I'd plot the 11.26. The 11.26 is more extreme. So it's in the rejection region. And so we reject. And we reject the null less than 0.1. So I just need you to be able to look at this summary table. If I give you a summary table, can you explain what I just said? I know I've got 3 levels of an independent variable. I know my F that somebody else came up with from this table is more extreme than this critical value of the P less than 0.1. So if you were going to interpret this, you would say that these averages of these 3 different levels are significantly different at the 0.1 level. I don't know where they are. I don't know if it's 1 versus 2. I don't know if it's 2 versus 3. I don't know if it's 1 versus 3. I don't know yet. I just know that they're not all equal. That's it. That's the F test. So here's another Anova summary table. So we got, let's talk about birds. So we got reinforcement schedules. You'd be surprised at how much research is done with birds. So we've got some reinforcement schedules here. So right now I see I'm dealing with a one-way Anova because I've only got one of these things, one independent variable here, schedules. Degrees of freedom equals 3, which means I know I've got 4 levels. So I got 4 averages that I'm comparing. I know I'm probably dealing with about 22 birds. This 17 is basically, this over this. So I've got an F obtained of 17.16. So how extreme is that? Well, if I needed to reject at the 0.5 level, I needed to be farther than 3.16. If I need to reject at the 0.1 level, I got to be more extreme than the 5.09. I'm way more extreme than any of these. Like I got 17 over here. So again, if I was going to draw a hump on the board, the 0.5 level would be 3.16. At the 0.1 level, it would be 5.09. And where I'd plot that 17.6 would be way over to the right and definitely in the rejection region. So I get to reject the null that they're all equal. And what's this idea between the 0.5 versus the 0.1 is that I want to know how significant I am. So I am less than 0.1. So the probability of getting all these averages, given that they're all the same, is less than 0.1, less than 1 in 100. So what does that mean? They're like, nope, these things are not all equal. Here's an example of how to interpret what this F test means. It says the schedule and reinforcement used during learning has a significant effect on the persistence of responding during extinction. Oh God, that's really boring. It is unlikely that the 4 samples have a common population mean. All right, so maybe you shouldn't copy this one in your mind. What you really should say is that the schedule reinforcement used during learning has a significant effect on whatever it is that they were talking about. So if they're responding during extinction, just responding. They're just responding. You don't need to say it's unlikely that the 4 samples have a common population. You can say there's a statistical significance between we reject the null that they're all equal. That's all you need to know. That's all you need to interpret at this point. You need to go further, but if you're just doing the F test, you would say we reject they're all not equal. So this very last question here, what else would you want to know? Well, what else do you want? I want to know which schedule. So I've got 4 schedules. Which one's the best? Which one's the worst? Which ones are not different from each other? So now you got 4 averages, but I want to know what those 4 averages are like. That's the next conversation. That's going to be the next PowerPoint slide. I just wanted you to start with the F-test to begin with. And it's nice that we have a breaking point because you basically have two tests in ANOVA. You got an F-test, and then you got the specificity of the different groups and that kind of stuff. So this is just one. This is just the F-test. There's a second part of ANOVA that we're going to have to do. So that's what the next part is, what answers this question. What else would you want to know? Okay, so this is the last slide of this go around, but this was the last slide of the entire chapter. But I wanted you to start being familiar with ANOVA assumptions. So again, this is when we can start poking holes in research, is because we assume things. And in order to calculate an ANOVA, we assume a lot of different things, which are not so good all the time. Honestly, we shouldn't make these assumptions, but people who do an ANOVA, so right now, if you're going to do an ANOVA in Excel or SPSS or whatever you want to find out, you're going to do an ANOVA, you're making these three assumptions right away. And if these are wrong, then theoretically what you're doing is wrong. But I need you to understand, in order to do an ANOVA, you need to assume three different things. This is just the one-way ANOVA. The factorial ANOVA next in chapter 13, we're going to add three more assumptions. But for a one-way ANOVA, I've got three assumptions. Normality. The dependent variable is assumed to be normally distributed in the population of which the samples are drawn. We assume the dependent variable. Let's just talk about test scores and booze like we were talking about earlier. So we assume that the dependent variable, test scores, is normally distributed in the population when it's drawn. So the people who had 0 shots versus 1 shot versus 5 shots versus 10 shots, the normality of test scores are normal within each of those groups. Like, I didn't cherry pick all A students and put them in the placebo group, and I didn't take all the really, really bad students and give them 10 shots and put them in that to justify that drinking decreases test scores. No, I assume that all the test scores are normally distributed in all those groups. The second bullet point, homogeneity of variance. Again, I told you the very first day of class, you're like, do you know what homogeneity of variance means? You're like, no, now we do. Homogeneity of variance. The variance of the dependent variable scores for each of the populations are assumed to be equal. So I assume the tests, so all right, so you're like, how is that different from normality? It's just slightly different. So the dependent variable for normality, dependent variables assumed to be normally distributed in the population with the samples are drawn. So not only homogeneity of variance is a little bit more like, did I cherry pick college students into groups, high and low and that kind of stuff. Normality is more along the lines of, do all college students have a normal distribution of test scores, let's say of stats? So if I'm going to be using only college students in my study, do all college students have a normal distribution of test scores? Yes. Homogeneity of variance is that if those four groups in my study, those four groups are also having equal, they all have equal variation within each other. So that's kind of, again, this idea that like there's normal variation that for all college students is also the same kind of variation within my specific groups. And this last one is that random assignment. It kind of gets this idea again about cherry picking, but these students were randomly assigned into groups. So that means that I'm really not trying to change the variance and control the variance between these two groups. So we assume that these people in these groups were randomly assigned, at least as best as possible. Why do we care about random assignment? It's because any sort of extraneous variable that's going to affect my dependent variable should be equal across all those groups. So let's talk about this virus that's going on right now. So say I was doing this research right now, randomly assigned, if everybody had the possibility to get in there, well, everyone still is being affected by this virus in relatively the same way. At least we're all going through it together at the same time frame. So what does that mean? The virus might be an extraneous variable for one person in the placebo group, but it also has a possibility of having an extreme effect on the person that's in the 10-shot group too. So that extraneous variables that everybody could be having should be equalized across all those different groups so that one particular extraneous variable can't have an effect on one group's average. It's having an effect on all the group's average. It's kind of that's what I'm talking about right now. This virus is having an effect on all groups at the same kind of level. All right, so I think that's it for the logic of Nova. I'm sorry this was really, really long, but you needed to stay with me for a little bit for this logic of the Anova. Next one we're going to talk about what's the next step in the Anova. The first step is to do the F test, retain or, retain or reject the overall F. Then we get into specific comparisons. So this is just step one. So watch the next video for step 2. Thanks.